All right, if we can go ahead and get started, please. As we recall back to one of our original modules, we talk about the goal of a Six Sigma process. Right? The goal of a Six Sigma process is to be a stable, capable process. The word capable means in specification. The word stable means, another definition for stable would be what? Consistent, repeatable, all right? In this class, we'll go a little bit further, and we will say that a stable process is one which is in a state of statistical control. And thus, we need to have a technique in order for us to evaluate whether our process is in a state of statistical control. And we're going to use SPC, statistical process control, as our method to do that. It is the, by far, most widely used method to address the issue of stability. Right? We can take entire courses on SPC, and some of you may have taken a university course on SPC. The reality of industry is almost everyone uses up to 6 charts. So there are 6 charts that cover the vast majority of applications out there. We're going to go through 4 of them today. We're going to go through the ones that apply to continuous data, things like process time or lengths or widths. And then we'll talk about those that apply to attribute charts, but there are some core charts that most of the time people use. Now, this issue of SPC and where it fits in DMAIC, it has the word control in it, and DMAIC ends with control. Therefore, it does make sense that the SPC charts could be used as part of the control phase. And this is certainly true. We'd actually argue that if we can, putting in an error-proofing device would be better. But if we need to monitor our process, statistical process control is a technique to do that. However, it's really arguably its most power in terms of DMAIC as part of the measure phase. Because one of the questions we want to answer in the measure phase is, do we have a stable, capable process historically? In order to do that, we will make a control chart. For that reason, when you're doing a DMAIC report, really, if you have historical data, the majority of DMAIC reports will have SPC charts, which we're going to talk about in the next 2 lectures, as part of the measure phase. Now, certainly you can use as a tool as analysis as well. It could be done as part of the analysis of the process. But this, in my mind, is really where it's of most value. Now, again, at the end of the process, we want to come up with a process monitoring plan, and certainly reasonable to use a suggestion of a control chart for the future, but we want to begin by understanding our stability. We'll talk about this idea of stability. We'll talk about some different charts. In this module, I expect you to learn 4 different charts. They go in pairs. X-bar, range go together, and individual moving range go together. Another big topic is this concept of the difference between common and special causes. We mentioned this a little bit earlier when we looked at run charts. We talked about sporadic issues being special causes or mean shifts. This is where we come up with our tool to help us do that. Questions before we get started? All right, lots of applications. Let's say we were to go out and measure some part. We measure some part. We might record distances, diameters, typically circle the line through it, maybe some depth or width measurements, various things we might measure on some product. Now, I'm not suggesting SPC only applies to manufacturing. It applies to anything that we measure as a continuous variable. I could easily do this with process time. All right, we're going to go out and have some measurements. In this case, we're going to measure everything as a deviation from nominal. I bring this up because this is actually quite common in the world of measurement. sometimes we don't really care exactly the raw value. We want to look at everything as a relative amount. It helps with the communication of things. In this case, we're going to measure everything to design nominal, what it's supposed to be, with a plus minus. That plus minus amount that is called the tolerance. In this case, we'll call design nominal 0, and we'll have plus or minus 0.7. So our USL will be what number? 0.7, and our LSL will be negative 0.7. Actually makes it quite straightforward. Now we're going to go out and we're going to collect some data from this process. And let's say we take data as groups of 3 for 12 different setups or 12 different batches. This is what's known as a subgrouping strategy. Instead of just measuring consecutively, I measure them in groups. I wait for some elapsed time. I measure them again. And if I do this, I could make a time series plot, and I could ask you, do you have any clear trends for this variable? And just by looking at a time series plot, is it easy to tell if you have trends? You might think, oh, it looks like maybe there is a trend there, right? But it's rather subjective. SPC is going to provide us rules to help take out the subjectivity. I would argue that it's hard to tell here. We want a tool to be more objective. Now, we ultimately may come back and evaluate our tool with some subjectivity and interpretation when it comes to the practical side of things, but we want to have an objective way to evaluate that initially. And this objective way is to use a better visual, and this better visual is going to be an SPC chart. All right, as an aside, what do you think makes more sense? Measuring 36 in a row or taking this subgroup of 3 and spreading it out over time? Which one do you think makes more sense?
Probably splitting it off into 3 spread out over time, because then you get like variation over the day or like different operators, so you can kind of see different effects.
Okay, very good. When you take a subgroup and spread it out over time, you actually get 2 things. You get a way to measure some inherent standard deviation based on consecutive parts, but you're also spreading it out over time, and you're giving the process opportunities for new operators to do something different or differences in the setup procedure. People sometimes say, how many samples do I need? And they say 30 or 40 because statistics say that's how it closely matches a normal distribution if the data is normal, right? In problem solving, yeah, 30 or 40 is fine, but if I had my choice, I don't just want to say 30, I want those 30 spread out. And I want to have some that are consecutive and then some elapsed time to give myself a better chance of seeing both the overall variation of the process as well as any inherent or within subgroup variation. And you have to kind of learn to kind of appreciate that to understand really why we do it this way, right? We're trying to take our data and we're trying to separate the overall variation into within and some between. So between subgroups versus within subgroups. Probably should put little variances there. All right, this is what we're looking to do. Now, how do I do that? Well, I got to have some understanding of this idea of common versus special cause. I then want to show you the generic control chart. And if you learn to kind of appreciate the generic control chart, after that, it's just which button do you press in Minitab. All of the charts are going to look similar. We're just going to change the statistic we monitor. But we're going to interpret them similarly. And so once we kind of get a sense of the generic, then after that, usually it's pretty straightforward, just different types of statistics to monitor. Since we're doing this in a little bit shorter approach, we're going to spend a little bit less time on this idea of coming up with the right sampling plan. I'll talk about it more conceptually and some general guidelines. And then I'm going to want to have you understand some different types of charts. We call this variable data. That just means continuous data, but most textbooks refer to this type of chart as variable data when they're talking about continuous data, so we'll use that language. And then we want to learn these in pairs: X-bar, range, individual, moving range, and then we'll explore some additional issues with another example. All right, SPC is not something that is new, right? It is not new to Six Sigma. SPC is a very old technique, goes way back to the 20s by a person named Schuhart, and he basically said every process has some inherent variation. This is due to the uncontrollable noise variables. I'll never be able to do everything exactly the same way. I can't even measure it exactly the same way every time. There's even variability in my measurement system. For that reason, I'm always going to have some inherent variation, of which he's going to call chance variation. His word chance later was called common cause by J.M. Duran. So we have common cause variation, is that inherent or by chance. And then there's variation which could be caused by doing something different, a mean shift. He called that an assignable cause. He said you don't just get data to shift. If data shifts, there's a reason for that. And you have to go figure out what that reason was. But his first step was, first tell me if you even have to go look. All right? So the idea here of SPC is to separate common and special causes. This is a key point. All right? Distinguish between common cause and special cause. And then he proposed a chart to do this. And this has since been kind of given as an analogy to how we look at the chart. If I was teaching you to play darts, and I was teaching you to, say, play a game like cricket or something like that, and you were all over the board, the first thing I'd try to get you to do is to become consistent. For example, if you ever play cricket, maybe the 20s are the easiest numbers to hit. So I would go and teach you to try to hit the 20s. If you could become consistent, then I can try to move you to the bullseye or move your aim once you are consistent. But the thought process of SPC is first get to be consistent and then try to adjust as necessary to hit your target. Now, sometimes you can go right from out of control to target, but a lot of times we have to first become consistent. In this idea of stabilizing the process, the question becomes, how do I know if I'm stable? And we're going to use SPC to answer that question. How we doing? We okay? I will certainly ask you questions related to that statement right there. To dig a little deeper, if I'm trying to distinguish between common cause and special cause, I want a little bit more of a definition. Common cause, we think about that as random, inherent, and predictable. If you have some inherent variation in the future, it's going to keep happening. Special causes would be things like mean shift with an assignable cause, an assignable trend, a spike. Spike is another word for sporadic condition. Oops. Sorry about that. And if I pictorially show that, if I have some variability, that's common cause. If that mean to that mean shifts, that didn't just happen by chance. There's some assignable cause is the way we would look at that. All right, there's a lot of words in this next slide. I'm not going to read these, but I want you to just pay attention to common cause, also can be known as the inherent, or you can think about this as the within group if I collect subgroups. Special causes, these are the changes that happen between groups. As an example, call these special causes. If I was in a non-manufacturing environment, maybe I have a new software system. Maybe I have a new employee. If I'm in manufacturing, maybe I change my setup procedure. You can read through those in more detail later. All right, pictorially, what do they look like? If it is a sporadic change or a spike, we think about what? We go along, and then all of a sudden, something happens. These outliers, if you will, are the sporadic changes in the process. What could cause a sporadic change? Something could cause this. Would be what? Anybody? Measure something, yes.
Like an employee in training.
All right, maybe I have a new employee who's in training, doesn't know what they're doing. It could be caused by measurement error. Maybe I measure something wrong. Maybe all of a sudden I drop something, damage something. But the point here is something that's related to kind of a lack of discipline. Then it kind of comes back. It's not really systematic. When it's a systematic shift, this would be when I am running along and then the whole process moves. And over here, if I were to draw x bar 1, x bar 2, x bar 3, something is causing that mean to move around. Maybe I have a 3-shift operation, and all 3 shifts think about it, have their own idea of what's the best way to set it up. So shift 1 sets it up, then shift 2 changes the setup, shift 3 changes the setup. In both of these cases, we may need to look at our standardized work. All right, the idea of an assignable trend, such as oscillation, let's say it looks like this. What do we notice about that graph? What does it do? Alternates up and down. Would we expect something to just randomly alternate up and down? No, we wouldn't expect just by chance for things to automatically randomly go up and down. Maybe a few of them, but if it does it over and over and over and over again, there's a pattern there. Classic example here might be 2 shifts. Shift 1 has one method, shift 2 has another method. And they just go up, down because they're not using the same. The point here is that there is some type of assignable cause to explain the pattern. Assignable cause to explain the pattern. All right, how are we doing? All right, in the next few lectures, including today, we will be discussing control charts as our tool. This is our tool to assess stability. We want to recognize that most, not all, follow a very similar format and use a common terminology. In fact, what I'm showing you here is what's referred to as a Shewhart control chart. Shewhart has its techniques and how he did set this up. All right, what we look for. First of all, we're going to make a graph, and we're going to plot points in the order in which we collect them. If these are days, our subgroups, it's going to be 1, 2, 3, 4. For that reason, you have to know the order in which you collect data. If you don't know, you cannot apply SPC. You can make a box plot or a histogram, and look for outliers, but you cannot apply SPC. SPC requires us to be in order. Everybody good with that? What changes on a control chart is the y-axis. The y-axis could be y bar, and y bar is the same as x bar. It just depends on whatever you want to label as the variable you study. The y-axis could just be y or x. The y-axis could be a proportion, percent effective. Different charts are going to change the y-axis. Let's say our y-axes are averages. Every subgroup is going to have an average. I'll use x bars, x bar 2, x bar 3. Then every chart is going to connect in sequence. The lines are going to be connected. We doing okay so far? You're going to plot whatever your statistic is. You're going to plot a statistic. Or technically, it could also be an individual value. Not a statistic, just the individual value. But you're going to plot a statistic or an individual value. Then what you're going to note is if I have a statistic or an individual value, that value is going to have some central tendency. What is the central tendency of x bar sub i's? If you have a bunch of averages, they're going to confirm or form around what? Yes? What do we call the averages of all the averages?
X double bar.
X double bar. Somewhere in your school, hopefully you had the case where they wrote 2 bars above the X or 2 bars above the Y. That's the average of the averages or the grand mean. So averages will flow into that. Then we're going to say, okay, well, if I have some measure of central tendency and there's some inherent variability of my statistic, I can set up limits where I expect the points to fall. And I'm going to set up limits on a Schuhart chart at plus or minus 3 sigma. But this sigma of x bars or sigma ranges or sigma p's, sigma something. We're going to call these UCL and LCL, upper control limit and lower control limit. UCL is not to be confused with USL. USL stands for upper specification limit. Specification limits are not control limits. They may not even be anywhere near each other. Right? Specification limits define capability. Control limits define stability. Now, our expectation is all the points will be inside the control limits. That will be in control. We'll have some additional rules as well. If a point is outside the control limit, we're going to call that out of control. And we're going to assume we have a common or special cause that drove that. Common or special cause would drive that. We're going to assume that we have some special cause, that it just didn't happen. Now, sometimes it may be a false alarm. This is the problem with, not the problem, this is the issue with statistics. We're not always right. But when points go outside of control limits, we're going to look for a special cause. Sometimes there may not be one. It may have just been bad luck. But most of the time, we should expect to find an out of control. Again, as I go through different charts, all I'm going to do is I'm going to change that. Instead of looking at the average, I might look at the range of a subgroup. Instead of looking at the average, I might look at the moving range compared to consecutive points. Instead of the average, I may look at the proportion or the defects per unit, something we discussed already as well. All right, questions? All right, a little bit of definition things. When I call something out of control, one or more subgroups outside the 3 sigma control limits. When I say 3 sigma control limits, do not fall for the idea that it means 3 sigma x's. It could be 3 sigma x's, it could be 3 sigma x bars. If I'm plotting x bars, I'm going to do 3 sigma x bars. If I have a P, I'm going to do 3 sigma proportions. So think about the subscript matching the statistic on the y-axis. We are also going to look at non-random patterns of behavior. What are examples of that? The following are all out of control conditions. 1 or more points outside the limit. If you get 9 consecutive points above or below the center line, we're going to call that out of control. Even if all 9 of those points are inside the upper control limit or lower control limit. You with me on that? Even if they're inside the control limits, if you get 9 in a row above or below the center line. Now you might think, well, why would that be? Think about it this way. Let's say you have a process and your mean is 5. What's the probability the next subgroup is going to be greater than 5? By chance, 50%. The next 2 in a row above that, 0.5 times 0.5, 25% chance. 3 in a row. At some point, the probability of that being by chance is going to be so low that you're going to call that out of control. That's where these come from. Now, people who write books say 9. Other people who write books say 8 above or below. This is just whatever the person writing the book picks as their threshold. Minitab uses 9, so we'll let the Minitab default for us. Are we okay? That one should make sense to you, above or below, even if they are all within the limits. Other examples. If you get 6 consecutive increasing or 6 consecutive decreasing, if you get 14 that go up, down, 14 in a row total would also be considered a special cause. Right? The idea here is if you have a very low likelihood of these things happening, we're going to call them special causes. In this class, we're going to use these 4 rules. I could buy different software products and they may give me more rules. What can happen, though, if you have too many rules? What's a potential worry if you have too many rules? Yes?
All sorts of stuff is out of control because there's just like too many rules that all suggest the same one thing.
Very good. You start to get too many things and you start to get a lot of false alarms. You start to get a lot of things that you call out of control, but then someone says, why is that? And you don't really have a good answer. And before you know it, people start to ignore you like you're being overly sensitive. Right? We're trying to find that right balance that when things change that really are a problem, we detect it, and other times we don't overreact. Too many rules can lead to excess false alarms. False alarm is when you say something is different when it's not. All right, let's jump back. In this class, any out-of-control condition we'll call not stable. We won't say close to being stable, near stable, almost stable. We got to draw lines. If you're writing your project or case study, you could say something like that. But in this class, anything that violates those conditions, we're going to call not stable or out of control. By the way, when I represent things as plus or minus 3 sigma, and they follow a normal, that means I expect all the values to be within 99.73. What that also means is that you're living with a false alarm rate of 0.27%, 1 minus the 99.73. That false alarm is when we say out of control when not. And if I tell you your confidence is based on 99.73, you can take 1 minus that, and that's essentially what your alpha error is. right? You know, before we often do alphas 0.05. We want to be 95% confident. In the world of SPC, we're actually going to have a tougher threshold. We want to be very careful about calling things out of control. As a result of that, we're going to make that alpha value lower. Now, I got to be a little careful because I don't want to prove every single control chart. The alpha value based on different charts will move around a little bit, but it's going to be low in almost all cases. We're not going to require you to know that, but just want you to understand that, particularly in an X bar chart, my alpha value is really typically lower than I might have if it was just a hypothesis test. I want to make sure that I really am out of control when I claim that. Everybody remember that the idea of alpha type 1? Remember that from before? All right, questions, or are we okay? All right. When I think about why I would even do this, one of the reasons to do this is to identify when I should adjust and when I should leave well enough alone. The famous statement, it was demonstrated by a person named Deming, that talks about the problems with over-adjustment. If you constantly adjust your process, you often make it worse, not better. And this has been shown over and over again. If you were to walk in, for example, in a manufacturing plant and someone produces a part, measures it, the part's a little bit big. They go and they automatically change the tool to try to make it smaller. They measure the next one, it's a little bit small, so they change the tool to make it bigger. If they are changing the tool every single time, they actually make the process worse. Sometimes the right answer is do nothing. We have some inherent variability. Don't compound the inherent variability by adding in over-adjustment as a special cause. We can also use to figure out when and how much to sample. If I work for a company and I measure, say, once a week, and I am never out of control, what might be a reasonable suggestion? If you measure once a week and you're never out of control, you might say measure every 2 weeks. If you measure once a week and you're out of control, someone might say, oh, we better measure every day. If we're still out of control, we might say, got to measure every hour. We think about how often we measure. Now, this is part of the subjectivity side of things, but if we go a little deeper in this topic, we can start to think about how much do I really need to measure being influenced by the idea of whether I am stable or not. The less stable I am, the more I measure. And if I am highly unstable, meaning I have lots of shifts all the time, I need to do 100% inspection. If I have very little change, I may not measure a whole lot, depending on the process. Right? I've been in world-class manufacturing companies that measure things once a month because they monitor their standardized work, and as long as their standardized work is being followed, they don't feel the need to do a lot of extra measurement. Other people are measuring every 15 minutes. Right? Even how much you measure does not affect your quality. It's how well you control your process. SPC becomes that assessment tool. If you want to go a little bit deeper on that, there are all kinds of videos out there on the Deming funnel experiment. It's a very classic experiment that illustrates this. I have some slides as well, but watch a video, 10 minutes, 15 minutes. Does a very good job. All right, we're going to move on. When we decide how we're going to sample, we want to recognize that on one hand, I want to collect data using large sample sizes, which could also be written as large subgroup sizes. If I measure larger subgroup sizes, I have more confidence in my findings. I can detect smaller shifts. This is reasonable. On the other hand, though, if I measure a lot, it costs me money. If I'm measuring a lot and I get no useful information from that, there's a reasonable argument to measure less. If I control all the inputs of the process, the output should be fine. Maybe I don't have to measure so much. This is the trade-off. I'm trying to find the right approach. Ultimately, I seek what's known as a rational sampling plan, something that, quote, makes sense. Some examples of this: I might measure 3 parts per shift. In this case, subgroup size would be 3 in a row every shift. I could measure 5, by the way, this would still be consecutive parts. I could measure 5 consecutive parts every hour. Subgroup size is 5, frequency is per hour. Sometimes I may decide to only measure 1 per day, or maybe 1 per month. This could be fine, kind of depends on how much change is happening. If I measure 1 per day, the subgroup size is 1, and the frequency is per day. All right, I'll let you read through this, but the idea is not that complicated. The idea of a rational subgroup size is you want only the inherent common cause to happen inside the subgroup. The reason I measure 3, 4, 5 is I'm expecting only inherent variability to be there. The idea of a rational frequency is I want to be frequent enough to detect important changes. But I don't want to be too frequent that I spend unnecessary money. This is the challenge. All right, one more thing about collecting data in subgroups. You could think about this as, all right, let's say I measure a subgroup and then I measure 3 in a row in every subgroup. I got n equals 3. Alternatively, I could have just measured n equals 1. The beauty of measuring n equals 3 is that if I take subgroup sizes of 3, each subgroup, x bar 1, then I'll have an x bar 2, an x bar 11, and an x bar 12. Are you with me? If I take subgroups of 3, I will end up with 12 estimates of means, a mean for every subgroup. Got that part? If you go back to school, in a statistics class, you should have learned the central limit theorem. Central limit theorem says, regardless of the distribution of x, if you're looking at the distribution of x bars from that, that will tend towards normal. X could be skewed to the right. But if I take subgroups of 3, and I have x bar 1, x bar 2, and I look at the distribution of x bar sub I, this is going to tend towards some normal with x double bar and sigma x bar. In fact, you probably learned sigma x bar is the same as, what's the name for that? What do we call that? And remember what sigma x bar is known as in the statistics? Don't like when I pull up your stat class? Did you ever hear the term standard error of the mean? Sigma x bar is the standard error of the mean. X bar sub I is going to be normally distributed with x double bar sigma, even if the underlying distribution is not normal. This becomes powerful. Don't worry about exponential, skewed, whatever. Multimodal will still be okay. Likely to be okay. Always exceptions. All right, how are we doing? We all right? Central limit theorem. We get to use it again. please internalize this as well. When we collect subgroups, we don't do 3, then 3, then 3, then 3. The idea here is to do 3, wait some time, do 3 more. Now, some people may just say every 3 I'm going to call a subgroup, and they do 10 subgroups in a row. You can still apply the tool that way, but it's not how it was really intended. It was intended to be spread out. It can be applied either way, but we intend it to be spread out. All right, this same thought process we're going to use over and over again. And we're going to learn some different charts. We're going to begin by talking about the case where y or x is continuous. Length, width, volume, time. Then, based on our subgroup size, if the subgroup size is 1, we're going to use individual moving range. If our subgroup size is 2 through 10, we're going to use x bar range. If our subgroup size is greater than 10, we're going to use what's called x bar S. I'm not even going to show that because it's very rarely done. But if you did take large subgroups, that would be the recommended way to show that. All right, let's begin by thinking about this continuous variable. And I want you to pay note to the fact that when you have a continuous y, such as a length or a time, we're going to make 2 charts. One chart is intended to measure within subgroup. The other one is intended to measure between subgroups. If our subgroup size is 2 through 10, this becomes very logical. If it's 2 through 10, we're going to use a range chart to measure within subgroup variation, and we're going to use an x bar chart to measure between. Think about it this way. I'm only going to draw 3 here, but if I did subgroup sizes of 3, for each subgroup, I'm going to get an x bar 1 and a range 1, x bar 2, range 2, x bar 3, range 3. I didn't write that kind of small, but hopefully you follow along that, right? If you measure in groups of 3, every group of 3, you can measure the range of those 3 as well as the average of those 3. The range of those 3 is used to monitor within group. The x bar is for between group. You okay with that? If we measure a subgroup size of 1, the between is going to be measured by looking at the individual values. That's the best I can do. Now here's the one that is trickier. If I have a subgroup size of 1, there's no way to measure within subgroup with a pure estimate because I don't have 2 from the same one. The best I can do is measure the moving range. Take the difference between each value and the next subgroup. Each value in the next subgroup. I'm going to use the moving range as the best I can do to measure within subgroup. It's not going to be the ideal case. And in fact, you could have some variability within a subgroup that is not detected because you're not measuring in terms of subgroups. You might say, why would I ever do that? Well, let's say you go make a part that costs $1 million. They may not let you measure 2 in a row. Costs very expensive. Let's say to measure something, you have to destroy it. You weld something, you want to measure the strength of the weld. Only way to do that is to destroy it. If you destroy it, they're not going to let you measure several. Maybe you're only keeping track of your month-end close number of journal entries. Well, I'm only having 1 number per month. I don't really have subgroups. There are times that I don't have subgroups, and the default is 1. But you have to understand this. It actually comes into play a lot because what ends up happening is you're not as sensitive. Your estimate of within subgroup variation could be wider than what you really is going on. How are we doing? We all right? Questions? All right, let's come back to an example. We have our subgroup. We got our 3 values. This is R1. How did I get R1? What did I take minus what? Just max minus min. The difference between negative 21 and negative 29, absolute value is 0.08. Then I've got R2 all the way down to R12. This is, hopefully, X bar 1, X bar 2. I'm just taking the average of those three. If I have a bunch of R's, I can compute the R bar. That's the average of the R's. If I have a bunch of X bars, I can compute the X double bar. That's the average of all the X bars. Also can call that the grand mean. On a control chart, those numbers are going to be center lines or control limits. On a generic control chart, those are going to be center lines or control limits. Center lines. This is the central tendency of my statistic. Ranges are going to have a central tendency to R bar. Means have a central tendency to X double bar. Are we okay? Or question? Both. There'll be a center line of a range chart. That'll be R bar. The center line of an X bar chart will be the grand mean. Make sense?
Yes, thank you.
Depends on the chart. Range or X bar. All right, moving along. Mini tab. Stat, control charts, variable charts, X bar. We'll technically select X bar range, but if we just looked at X bar, that's the subgroups in order. The y-axis says sample mean. That's X bar sub I, or if you could call it Y bar sub I, either one. See where it says X double bar? X double bar is 0.2356. That's that number. Then the software makes 3 sigmas. This is plus 3 sigma minus 3 sigma. But sigma what? Sigma X bar, sigma P, sigma X bar. Very good. Plus or minus 3 sigma X bars. Sigma X bar is the standard error of the mean. You may remember from a stats class, that is the standard deviation divided by the square root of n. So sigma X bars is tighter than sigma X. The standard error is going to be tighter. But we're not plotting X's, we're plotting X bars. We make our control limits, and in this case, we get the following. We're going to call this out of control. Why do you think it has a 1 there? Guesses?
Reasons it can be out of control, and that's to like 1, like it fails to 1 test or something.
Very good. There can be different reasons. In this class, I gave you how many rules? 4 rules. That's rule 1. Other ones could be rule 2. It could be a rule 3. It could be a rule 4. This is a rule 1 violation, not first subgroup out of control. Rule 1 violation. That's kind of typical. In this class, under the estimate tab, if I make an X bar range chart, I'm going to tell the software to use the R bar method. There's some different defaults. For purpose of this class, I'll show you that coming up. There's a little click button that says R bar method. Just do it to be consistent with my solutions. All right, I want to know what plus 3 sigma X bar is equal to. I need a technique to calculate that. I need a technique to calculate that. All right, as a reminder, depending on the statistic, the limits are either going to be 3 sigma x bars, 3 sigma ranges, 3 sigma x's if it's individual, 3 sigma moving ranges. To get these numbers, I'm going to use estimation techniques that are found in books. In this class, I'm just going to let Minitab do it for me. I'm not going to go through the details of these. I'll give you a couple of them that are used very widely, but we'll let the software do these for us. I don't want to go too deep, but I'm going to go as far as this goes. In order for estimations to happen, there are a couple of well-known relationships. If you think about as the range gets bigger, the standard deviation has to also get bigger. There's a relationship between ranges and standard deviations. And based on the number of samples that I randomly take, this relationship converges. It converges to a constant in case of what's known as D2. And how this comes into play is that there are books that have constants in there. These are relationships to help us estimate terms. In the case of, if you want to tell me what sigma within is, I can use R bar over D2 for some n. In this example, n equals 3. If I put in R bar and the 1.639, I will get a sigma within of 0.059. I'll go one step further. If I want to go to sigma x bar, that's the standard error, that's sigma x over square root of n. Remember that from the stats class, maybe? If not, that's what it is. If I know what sigma x is, and I have n, I can convert that to a sigma x bar. This is what the software is doing. We'll let it do it for us, but we want you to have some idea of what's going on. All right, we're going to go ahead and move on. Now, there is manipulation. So 3 sigma x bars is really only based on R bar and the subgroup size. And I can do some manipulation, and there ends up being this formula, A2 times R bar. And if I go back to my chart, you will notice that for a subgroup size, there's a value for A2. This is, I won't do the proof. You can go to the appendix if you want. But this is just a manipulation of the formulas I just showed you. We'll let the software do this for us, and it will make the limits. What is important is I go from there to there. In this chart, I said, is this stable? It was hard to interpret. In this chart, if I ask you, is this process stable, what would you conclude? Yes or no? You would conclude not stable. Based on? This out of control condition. Hopefully you're seeing that this is going to be more objective. Now, very important. Do I know why I'm out of control? Do I know the root cause? No idea. I'm just getting a tool to separate common and special cause. To figure out why, that's a whole different analysis. That is another analysis. SPC is just separating common and special, giving me an objective way to do that. I then will try to figure out why that is as a separate analysis. All right, how are we doing? We all right? A range chart. The center line of the range chart is R bar. control limits are going to be plus or minus 3 sigma r's. Should be careful there. So r bar plus or minus 3 sigma r's. Now to get 3 sigma r, I'm going to use some other assumptions. So yada, yada, yada. I'm not going to go through the proof, but it works its way into a D3 or a D4. These are constant terms from this same table. And I get control limits. What is interesting about D3 for 2 through 6? They're all zeros. Now think about what that means. If I measured only 3 things and I got the exact same value every time, the range would be 0. That is not viewed as out of control. Let's say you measured 10 times. You measured 10 different units, and you got continuous data now, exact same value 10 times in a row. We would actually assume that that's not likely to happen, and you'll end up getting a below the lower control limit, because your value is going to be 0. Probably a measurement error, probably an assignable cause. All right, why do you think this is 0, though, for D3? Any thoughts on why that is set at 0? Why it's not a number? Let's say I run a formula and I do r bar minus 3 sigma r's and I get a negative value. What would be the problem with that? If I took minus 3 sigma r and I got a negative 0.1, what would be the problem with that? What is it? Ranges can't be negative. Therefore, the software just sets it at equal to 0. Right? There's a physical limitation here. The reason why this chart is not symmetrical, it's not that I can't calculate some number down here. It's that I can't have negative ranges. The software calculates a negative value, it just sets it as 0. I bring this up because it's not, looks symmetrical, right? You may wonder why it doesn't look symmetrical. That's why. All right, again, r bar, we got it from before. We set up our control limits, plus minus 3 sigma r's. We convert that using the D3 and D4 constants. In this case, is the range chart stable or not? Yes. You think it's possible for one chart to be stable but not the other? Absolutely. Your within group could be consistent, but your between group could have a change. All right. In this case, we may conclude that the x bar is out of control. The range is in control. In control is the same as stable. And when I say out of control or in control, I really mean out of statistical control. All right, these are our 2 graphs. The software is going to make them at the exact same time. But which chart should we really evaluate first? The x bar or the range? Which chart should you really look at first? Think about the formulas. Which chart should I look at first? Thoughts? What do I notice about that formula? It includes r bar. if my range chart is out of control, what do you think is going to happen to my estimate of R bar? It's going to be bigger or smaller? If my range chart is out of control, and we'll assume that it's in the upper side, is it going to be an R bar going to be larger or smaller? Larger. If R bar estimate is based on out of control points, I am inflating my estimate of R bar. And if you inflate your estimate of R bar, what are you doing to your control limits for the X bar chart? They're going to go bigger. I'm making my hands go wider. All right? So if you have a range or an R bar which is based on out of control ranges, you're going to say that the average R bar is a larger number than really what it should be. And then you're going to take your X bar chart and make those limits wider. And then you might miss some special causes, or you're going to miss some shifts potentially. For that reason, we want to examine the range chart first, because our R bar is going to be used with the establishment of the limits. There's a phrase for this. Many of you had a statistics class before. If you did like a two-group test, like an F test and a T test, typically you evaluate the variances before the means. If you took a class with analysis of variance as a technique, you evaluate the variances before the means. This is known as homogeneity of variance, HOV assumption. Homogeneity of variance means the variability within a group is consistent before I go evaluate mean differences. This is used over and over again in statistics. First, get that to be range first. Now, again, the software is going to do them at the same time. You just have to kind of know that this is logically what we should do. We all right? All right. Individual moving range charts. Don't overcomplicate this one. Subgroup size is going to be 1. What's tricky, though, is although the subgroup size is 1 for the individual, for a moving range chart, it's actually a subgroup size of 2 because it's going to be based on consecutive subgroups. Here's the case where you have a different subgroup size, even though it's a paired chart. The reason that people do individual charts, they would typically tell you because the cost of inspection is high, such as destructive testing, or you don't really have subgroups involved in that. What I would call an unadvertised reason is that an IMR chart is a less sensitive chart. And if you want to not be as sensitive at detecting small shifts, it becomes a useful strategy. Now you might say, why would I not want to detect shifts? If you detect shifts where people have nothing they can do about it, then you start saying, you're out of control, you're out of control. What do you want me to do? Nothing. Eventually, it doesn't always work as an effective tool. Sometimes we want to be less sensitive. The goal is to identify the big shifts, or when we want to change. Some processes we want to detect small shifts. Other processes we may be happy to detect large shifts only. It kind of depends on what you're trying to do. All right, let's illustrate this one. Let's say for our same data, we're using the same data, but we're going to use observation 1 only. I've only got 12 data points here. I can get these 12 values. The center line of those 12 values is going to be the mean. Now I'm going to need moving ranges. Moving ranges is just the difference between consecutive points, absolute value. You'll notice that there is no moving range for subgroup 1. Why is that? Nothing to compare. You have to start with subgroup 2, and subgroup 2 versus subgroup 1. Moving ranges formula-wise, is going to be based on n equals 2. Again, this is not a pure estimate of within subgroup. It's the best I can do. If I take this same data and I get a moving range, and I use my R bar over D2 formula, my sigma within is 0.087. Everybody see that? If I went back a few charts, what is happening? When I did the subgroup size of 3, my sigma within was 0.059. Why do you think this number is going up? I probably have some small between group, but it's being folded into the moving range. And the result of that is the moving range is being a wider estimate of the inherent. If the moving range is a wider estimate of inherent, what's going to happen to my control limits? Conceptually, they start to get a little bigger. That's where they become less sensitive. Let's go ahead and do this chart. If I looked at observation 1 only, as n equal 1 for the individual chart, what would I conclude? Stable. Stable. I am illustrating to you that individual charts may be less sensitive to detect small shifts. Now, if I had a huge shift, I'd probably still pick it up. This does not seem to be large enough. If this jumped to a plus 0.7, I'd pick that up. I didn't pick it up in this approach. I will certainly ask you questions to reinforce this idea. Helps us understand the differences. Let's do a different example. Let's say you have a healthcare example where you're keeping track of the number of surgeries per day. Now, in this case, I'm not going to have subgroups. I'm just going to have n equals 1. And because of that, I make an IMR chart. And what would I conclude here? Am I in or out of control? In control. In control. Stable. Now, this is important. Because my process is in control or stable, what would I predict as my number of surgeries per day on day 21? I want you to predict throughput on day 21. What would you predict as your throughput? Anybody? You're going to predict what is your average, right? Because you are in control, you have a predictable process. You're going to predict 32 and between 24 and 40. Because you're in control. That's one of the powers of this. Now, you may not like that answer. Maybe your goal is a throughput of 50. You may not like your answer, but you have a predictable process. I use SPC to determine if I have a predictable process. If I was out of control, what would you predict as the next mean of subgroup 13? What would you predict as the next mean for subgroup 13? You would not predict. The process is not in control. We don't make predictions. That may be if I was forced to, it's different, right? But the concept here is if I'm out of control, we don't make predictions. We make predictions based on an in-control process. I've demonstrated that I'm stable. How are we doing? We okay with that? All right, let's walk through an example, a little bit more detail on the Minitab commands, basically repeating the same concepts though. Let's say you go out and you have a subgroup size of 5. Every day you take 5 consecutive units and you measure the order fill time. So time is my variable. We also have an upper specification limit of 4. If I am in the DMAIC process and I'm in the measure phase, these are my classic questions. If I've taken in subgrouping, so I have a subgroup approach, I'm going to ask myself, is the range stable within a subgroup? Is the mean stable? And then I'm going to ask whether or not I am producing any out of specification orders. This is the issue of capability, and this is the issue of stability. Whether I have a stable, capable process. To do control charts, stat, control charts, pay note to that. You have variable charts for subgroups, variable charts for individuals, attribute charts. We're going to begin with variable charts for subgroups. We're going to select the X bar range. Typically make these as a pair. Again, we examine which one first though. Range chart first. You have to become comfortable in Minitab with 2 classic formats. We have format 1, where everything is a row, represents a subgroup. Format 2, you would have a subgroup ID, 111, 222, and then you would have values. In other words, you'd have a big column of values and another column where you have the different subgroup IDs, or a constant like every 3. That's different than when you have a row as a subgroup. I'm going to give you data in both formats. You've got to figure out which one to use in order to set up the chart correctly. In this case, we have a subgroup is a row of columns. Just kind of get used to the terminology. It's not that complicated most of the time for most of us. We've got sample 1 through 5 are our subgroups. If I have a row of columns, do I have to tell Minitab what the subgroup size is? No. If I give it 5 columns, Minitab knows that n equals 5. All right, a couple of things to note. Under X bar options, I'm going to select the button that says use the R bar method. If you were doing your own project in the world, doesn't matter which one you pick. They're just 2 different ways to estimate. For consistency, I taught you the R bar approach. That's what we're going to use. Where it says tests, you will notice that you have 4 check marks. These are the 4 rules. Those are the default values, 3, 9, 6, 14, same as my slides. If you want to change them to 4 sigma limits, you make that 3 or 4. But in this class, we'll use the standard rules. This one you got to be careful because a lot of software does not default to the 4 rules. A lot of software will only have the first rule. You'll have to change that to be 4 rules. There is a preferences command to change it for you, but you need to make that 4. All right, we go ahead and we run the chart. Questions are mean and range. We'll do the range chart first. Is the range stable? Yes or no? Yes. Is the mean stable? No. Is the mean out of control? Yes, the mean is out of control. What do those ones mean? Violation of Rule 1. What would you predict as the future range for the next subgroup? .96. How about the next mean? What would you predict? I would not predict. Unless I was able to figure out what those special causes were for, remove them from the data, but as a chart from here, I would not predict based on this chart. Are we okay? All right. What was my USL? Four. Are we producing any out of specification orders?
This is the classic trick question that every professor will ask you in your life. But it's a trick question. Why is it a trick question?
You can look at that X bar chart and you can notice that none of those sample means are above 4, but what's the problem? What are you plotting on the y-axis? You're plotting averages. You're plotting averages. You can't look at an X bar chart and make a conclusion about an individual value because you're not looking at individual values. You're plotting X bars. Every SPC professor will ask you this question because it's very important to understand that control limits are not spec limits. It's a way to ask that. Now, I will say this. I will ask this, and some of you will get it wrong. I'll ask it again. Some of you will get it wrong. But I told you in class today that I will ask you this question. I don't know what else I can do. All right. Control limits are not the same as specification limits. If I took this same data, I might have had one out of spec point. Also, if you're out of control, we're also less confident in our prediction of the future. Fitting a normal curve and predicting the expected ppm, for example, not as useful to do. If I want to know what the percent in spec is, we're going to come back to our tool that we used before, process capability analysis. And next time you do process capability analysis, you will notice that it wants the data in one of two formats, either a subgroup cross a row, or it's going to ask you to put them in terms of a big column. And there's also what's called the 6-pack tool, which does both capability and an SPC chart in the same tool. I'll show that again in an upcoming lecture, but there's also a capability analysis 6-pack that does both SPC and the capability in the same time. All right, some main takeaways today. Make sure you are grasping the idea of common versus special. This idea of trying to be frequent enough to detect changes. Understanding which chart to use, whether it's individual moving range or X-bar range. Recognize if you're doing an X-bar chart, you're not plotting individual values. Specification limits are not control limits. I showed you the same data was in control versus out of control, depending whether you use an X bar or an individual. I can do all kinds of examples to show you that I can make assumptions to make data look in control versus out. We've got to be clear on our assumptions, try to be the most representative. All right, that's it.